Welcome to the STEM Sessions podcast. I am Jarl Cody, your host and narrator. For the longest time, I was the lone member of my immediate family with no tattoos. I had nothing against them, mind you. I just couldn't think of any design I'd want permanently embedded in my skin. But that changed a few years ago. I'm not sure why, I just got the bug. Of course, me being me, I had to research everything about the process before I sat down for my first tattoo. What's in the ink? How likely are side effects? How does a tattoo machine work? What makes a tattooer a good tattooer? What is the history of tattoos? What are all of the styles? How do you keep a tattoo looking its best as the years go by? And of course, why does a tattoo stay in place to begin with? That last question, I'll answer now. And, by the way, if you're wondering, my tattoos are the best in my immediate family, by far. This is the STEM Sessions Podcast, Episode 3, Tattoos. Biological stalemates. Skin is a complicated organ. It prevents fluid from entering the body and regulates how much fluid exits the body. It contains pigment, oil and sweat glands, hair follicles, nerves, blood vessels, and immune cells. It regulates body temperature. It's self-repairing and self-rejuvenating. And it's a physical barrier to foreign pathogens. Depending on the location of the body, thickness of human skin varies from 0.5 millimeter to 4 millimeters, or 0.02 inches to 0.16 inches. The thinnest skin is typically your eyelids. Here, the thickness is equivalent to the stack of 5 sheets of paper. The thickest skin is typically on the soles of your feet and the palms of your hands. In those areas, the thickness is equivalent to a stack of 2 nickels. The outer layer of skin is called the epidermis. In the deepest part of the epidermis, cells called keratinocytes continuously undergo cellular division. As new cells are created, the older generation is pushed towards the surface. As these older cells die and reach the surface, they harden with a protein called keratin. It is this outer layer of keratin-infused cells that waterproofs your body and is the physical barrier against external bacteria, viruses, and other pathogens. These older and hardened cells constantly flake away, being replaced by the next generation of cells underneath. It takes 4 to 5 weeks to complete a full cycle, from cellular division to hardening to flaking away. Under the epidermis is the dermis. Roughly 3 times thicker than the epidermis, this layer contains sweat and oil glands, hair follicles, nerve fibers, and blood vessels, all held in place by a substrate of elastin and collagen produced by cells called fibroblasts. In addition to providing structure, elastin and collagen give skin its elasticity and strength. Unlike the epidermis, the dermis layer does not shed. Its cells and materials regenerate, of course, but the network of fibers keeps the new material locked in place, while older cells and debris are swept away via the lymphatic system. It's the dermis layer that holds the tattoo ink. When a tattoo is created, needles pierce the epidermis, embedding ink in the dermis, where some is absorbed by the fibroblasts and the rest is held in place by the network of proteins. Any ink in the epidermis will flake away with the shedding skin cells. In fact, that's partially responsible for the ink flakes you might see as your tattoo heals. And that's also why a tattooer's skill and experience is so important. He or she needs to properly gauge the depth of the ink placement. But let's dive into the details a bit. As far as the body is concerned, tattoo ink is a foreign invader. It's not a pathogen like a bacteria or virus, but it's still not supposed to be there. Further, a fresh tattoo is essentially an open wound. Your skin has been scraped and poked thousands of times by very fine and very sharp needles. The presence of the ink and the damage to the skin both trigger a response from your immune system. White blood cells, or macrophages, rush to the wound site, where they identify the ink as foreign particles. The bulk of the ink globules are consumed by white blood cells, becoming quarantined within their cellular walls. However, some ink particles are too big for the macrophages to consume, so they remain freely suspended in the dermis. When a macrophage consumes a pathogen, it releases enzymes to neutralize and break down the pathogen, rendering it inactive. The remnants of the pathogen in macrophage are then swept away by the lymphatic system. But when the macrophage consumes the globules of ink, the enzymes are not capable of breaking it down. Because it can't neutralize the ink, the macrophage keeps it locked in place, sequestering it from the body's fluids and tissues. Fortunately for fans of tattoos, macrophages and the epidermis are transparent. Thus, the tattoo remains visible to the outside world. Additionally, dermal macrophages lose the ability to move around or out of the dermis once they've consumed the foreign substance, so the tattoo geometry stays as the tattooer left it. This has been the accepted theory for quite some time. The tattoo is comprised of free ink globules and the ink-stuffed macrophages, all held in a stasis within the dermis. But an article in the Journal of Experimental Medicine from 2018 entitled "Unveiling Skin Macrophage Dynamics Explains Both Tattoo Persistence and Strenuous Removal" adds more detail. In a mouse study, the authors selectively killed ink-filled macrophages. When the macrophage dies, its remnants are flushed away, but the ink is left behind. Surprisingly, they observed new macrophages enter the dermis to reconsume the newly freed ink. Being unable to break down the ink, the macrophages again simply hold it in place. This ongoing immune response, one intended to remove the ink, actually helps maintain the tattoo. From the paper, quote, "The macrophages found in the dermis of adult mice are continuously replenished from circulating monocytes to compensate for the loss of dying macrophages," unquote. Further, quote, "Most of the tattoo particles that are released from macrophages remain in situ and are recaptured by incoming macrophages," unquote. The authors refer to this process as the pigment capture, release, recapture model, and it's this process that ensures the macroscopic stability and long-term persistence of tattoos. This isn't to say tattoos are 100% permanent, of course. Tattoos obviously fade and blur with age due to many factors such as the type of ink used, the skill of the artist, and exposure to ultraviolet light. And even if all of those risk factors are minimized, fading and blurring will still occur because it isn't just the macrophages working on the tattoo. The smallest of the ink globules are swept away over time by the lymphatic system, eventually leading to noticeable degradation. In fact, this is why laser tattoo removal is even somewhat possible. The laser breaks down the larger ink globules into bits small enough the lymphatic system can remove. Though with some types of pigments, lasers simply cannot break the globules into small enough pieces, which is why laser tattoo removal is often not fully successful. And even when the pieces have become small enough, this study has shown macrophages recapture the pieces and hold them in place before the lymphatic system can remove them. Therefore, the authors suggest the tattoo removal process may be improved by disrupting the macrophages from recapturing the pigment, allowing more of the ink particles to be flushed from the dermis. It's important to note this capture, release, recapture process has only been observed in mice, so its occurrence in humans remains to be determined. But I wouldn't be surprised to read of a study that makes similar observations in humans in the very near future. Thank you for listening to this episode of the STEM Sessions podcast. I do my best to always provide accurate information, but unfortunately, I'm fallible like everyone else. So I encourage you to do your own research on the topic we discussed. Corrections and new information are always welcome. Show notes, contact information, and details of our other activities such as meetups can be found on our website, www.thestemsessions.com. If you receive value from this episode and wish to give some back, please visit thestemsessions.com/value for value for ways to support the podcast. And most importantly, please remember that STEM is not the exclusive property of experts, policymakers, or talking heads. Every presenter is susceptible to bias unconsciously or deliberately. So always verify what you read and what you're told. Do your own research, satisfy your curiosity, and keep learning.